everyone. Welcome to the lesson of maxima and minima, collectively known as extrema, of functions of two variables and saddle points. The word maxima is plural for maximum, and this minima is plural for minimum, and extrema is the plural for extremum. Maximum and minimum of a function collectively known as extremum, and word we use extrema, that is plural for extremum. There are largest or highest and smallest, like this one, smallest or least. Value of the function either within a given range, that is known as local or relative maximum, and a local or relative minimum, while largest value and smallest value in the entire domain, that is known as global or absolute maximum and global or absolute minimum in the entire domain. So for ordinary function we have global and global maximum and global minimum, local maximum and local minimum, like this way. Now if we see maxima and minima functions of two variables, generally known as several variables. So three mutually perpendicular axes are here, and we have a surface, and topmost value on the surface, that is absolute or global maximum, and second topmost value, that is local maximum, and smallest value is absolute minimum, and second smallest value is relative minimum. Here we have definitions for relative maximum and absolute maximum in the definition 1, and in the definition 2 we will see relative minimum and absolute minimum. So a function of two independent variables x and y has relative maximum at the point AB if function value at point AB greater than or equals to function value at xy for all points x and y in some region around AB, and function value at point xy is said to have an absolute maximum at the point AB if FAB greater than fxy for all points in the domain of f. So here it is absolute maximum for the domain. Now we see definition 2, a function has a relative minimum at point AB if function value at the point AB is less than or equals to function value of xy for all points xy in some region around AB, and fxy is said to have absolute minimum if this condition holds in the domain of f. Now we see critical point. Let a function of two independent variables which is differentiable on the open set containing the point AB. Then the point this AB is critical point if one of the following two conditions hold. First partial derivative at point AB equals to 0 and first partial derivative with respect to y at point AB equals to 0. And second condition is either of first partial derivative with respect to x at AB or with respect to y first partial derivative at point AB does not exist. So here is the example. Find the critical point of this function. We differentiate this function partially with respect to x, with respect to y, treating one variable as a constant. So this is the result. Now for critical point, equating this one equals to 0, putting this equals to 0, and solving these two equations, we get x equals to 2, and from putting this one we obtain y equals to -5. So this is the critical point. Now we have extreme value theorem. If function of two independent variable x and y is a continuous, unclosed and bounded set R, then function has absolute maximum and absolute minimum on R. If any condition of extreme value theorem does not hold, then function may or may not have absolute maximum or absolute minimum on the region R. Also, a discontinuous function on a closed and bounded set need not have any absolute extrema, that is maxima or minima. Also, a continuous function on a set that is not closed and bounded need not have any absolute extrema. Now we have saddle point. If the function of two independent variable x and y has neither, this is a saddle point at point AB, if function has neither of relative maximum nor relative minimum at point AB. Now we see how can we find maxima minima functions of two variables. So for finding maximum and minimum, this is the working rule for obtaining maximum and minimum of functions of two variables. So let us consider we obtain maximum and minimum of functions of two variables at point x equals to a and at point y equals to b. So these are the steps we obtain maximum or minimum or neither the case. So R is the double differentiation at point AB. S is double differentiation of function with respect to x and y. So we can say S is the differentiation of function f with respect to x and y at point AB, and T is the double differentiation of function with respect to y at point A and B, and then calculate RT minus S square. And if rt minus s square greater than 0 and r is negative, then function is maximum at x equals to a, y equals to b. And if rt minus s square greater than 0, r is positive, then function is minimum at x equals to a, y equals to b. And if rt minus s square, from here we can see rt minus s square less than 0, then function has saddle point at point A and B. And if this value rt minus s square becomes 0, equals to 0, then no conclusion can be drawn and further investigation required. So we leave this case. Now look, another example for finding maximum minimum values and solve this question and examine for maximum minimum of the function. If exist, find the value. So let us see the solution. Now this is the solution of the given problem. For maximum or minimum of function f, we differentiate partially because function is of two variables x and y. So we differentiate function with respect to x, partially treating another variable as constant. So del f for del x is this one, del f del y equals to this one. Equating these two first partial derivatives to 0, we obtain x equals to a, y equals to a after simplification of these two equations. And these points where first partial derivative vanish gives a point, and these points are known as stationary point. So simply a comma a is the stationary point where first order partial derivative vanishes, becomes 0. Now our step 2, calculate r, s and t. Double differentiation of f with respect to x partially. Similarly s, similarly t with respect to y. Now we have obtained the point x equals to a and y equals to e. So at the point this AE, calculate r value, s value and t value. R is 2, s is 1, t equals to 2 at point AE. And next step is calculate rt minus s square. So rt minus s square is 3, which is greater than 0. Now according to our step 1, if rt minus s square greater than 0 and r is positive, then function is minimum at x equals to e and y equals to e, which we have obtained this point. And function is minimum, therefore we will obtain the minimum value at these points. So minimum value of function at point E, any x equals to E and y equals to E, on putting this value A and E in function, we obtain 3a square. This is the function minimum value of the function. Now we have some practice questions. So these are some practice questions, so that the distance L of any point xyz on the plane 2x plus 3y minus 3 equals to 12 from the origin is given by this one. Also find the point on the plane that is nearest to the origin. Simplification gives us these points. This is the answer. Second question, locate all the relative extrema and saddle point of function. This function simplification gives us at the point 1 1 and minus 1 1 relative maxima and saddle point at point 0 comma 0. So one can solve these problems easily. Facing problem, you can comment so that we will provide you a hint or detailed solution of these problems. Thanks for watching.